Just as a quick aside, if you're familiar with matrix multiplication, there's a very nice connection between this little algorithm that we were just working on and matrix multiplication. So the first thing to appreciate that, the first thing you need to understand is that if we can represent a graph on a set of nodes as a matrix, and it's a matrix that consists of all zeros and ones, and if it's a sparse graph, say mostly zeros. But if there's a link between node I and node j, then the corresponding position in the matrix has a number in it, a number 1. Right? That 1 there means that there's a link from I to j. Now, the graphs that we've been talking about, links are bidirectional. So if there's a 1 in this ij position, then there's also a 1 in the ji position, which in this picture seems like it would be really nearby, which means that this matrix is symmetric. And I'm not going to get into matrix terminology, but again, if you're familiar with it, you'll recognize what a symmetric matrix is. The matrix equals its own transpose if we flip things the other way, which is basically natural. I mean, if we're just interchanging the nodes, since the connections are bidirectional, we'll have the same matrix again. So let's call this matrix M, and let's think about what it means to multiply M times itself. In matrix multiplication, the way we fill in the ij entry of the product, so we take the ith row of the first matrix, and the jth column of the second matrix. And I always need two hands whenever I think about matrix multiplication. You go across this one and down this one at the same time. And what we do, in this case, since it's all zeros and ones, and it's a square matrix, what we're going to go through and figure out, anywhere where there's a 0 in one and a 0 in the other, it's going to be 0. Only if there's a 1 in both is it going to be a product that's not 0. So this multiplication of this row times this column is exactly a count of the number of ones that the two vectors have in exactly the same positions. Now, what does it mean for them to have a 1 in the same position? Let's check. Let's imagine that there's a 1 in position k here, and at the same time in position k here. This position here means that our graph has a link from I to k, right? That's what this means, if there's a 1 there. And similarly, if there's a 1 in this position, it means that very same graph that we're talking about, this graph that M is representing, also has a link from k to j. And what we're doing is counting up all the k's that have the property that they would take us, you can get from I to one of those, and then to j from one of those. So it's going to add all those up. That's exactly what matrix multiplication does. So this value here is going to be filled in with precisely the number of two-step paths from I to j, which is exactly what we needed in that other example, that we're basically counting up the comic books that are in common between some character I and some character j. So in the case of the bipartite graph of the Marvel comic book characters, any two-step path that starts at a character goes through a comic book and then a character. So this is counting up exactly the number of comic books that I and j are both in. So there we go. The square of the matrix, which represents the connections of the graph, actually gives us the same answer. The running time of this algorithm, of course, is n cubed, because we're looping through for each of the entries of this matrix that we're going to fill in, and there's n squared of them. We're doing this row by column multiplication, which also takes time n. So it's n cubed. The algorithm that we've just been talking about is something more like number of edges times the number of nodes. The number of edges here comes from the fact that we loop over each of the character book combinations that we have stored explicitly. And then for each of those, we examine which characters are they're connected to. So it could be as bad as n times m. If m is dense matrix, then this is n squared. So this algorithm ends up being n cubed again. But if it's a sparse matrix, so the number of edges is linear, like in a planar graph, for example, then this is n squared, which is actually a lot better.